We are studying kinematics of machines, and that is essentially how to analyze, achieve and control the motion of machine parts. And in this connection we have studied various arrangements like mechanisms, belts, chains and various types of gearing. Kinematically speaking, each of these gave us a specific input-output relationship, which we quantified in terms of the velocity ratio. And except for gears, where we successfully kept it constant, it was a very difficult quantity to control. So here we are going to look at an arrangement which allows us not only to control velocity ratio, but achieve a lot more than that. We'll be able to control the displacement, the velocity, the acceleration as a function of time or a function of displacement of another machine part. The basic idea that we are going to use to solve this problem is very simple. Suppose we have been given a displacement against time graph, which is to be achieved so that a machine part moves according to this function against time. What we do is we take this graph, we cut it on a physical plate, maybe a thick metal plate. Then the part which is to be moved according to this function is made to rest on this profile, and it is constrained with help of some support so that it moves only up and down in the y direction. Now if we set this plate into uniform motion along the x-axis, then the part which is resting on it will follow the displacement against time function that we are trying to achieve. This metal plate, this particular profile, is called as the cam, and the machine part which is following it is rightly therefore called as the follower. So in theory we have solved the problem, and the solution that we just got is called as the wedge cam. But there is a small problem here. Not for lifting this up or in the rise of our follower, but when it comes down, so when it is returning. Suppose we want to achieve an acceleration greater than g, the gravitational acceleration, in the downward direction. In that case this arrangement will not work because our follower is simply resting on the cam. So at the most it can fall freely under gravity, but it will never achieve an acceleration more than that. So for that we use a different arrangement, say the same profile cut like a channel on a thick metal plate. So it is capable of not only pushing the cam, pushing the follower up, but also pulling it down. So the plate cam is more reliable, especially in high-speed machines where the acceleration could exceed gravity. Now to make it more compact, we can have this whole graph wrapped around a circle. So as it moves, it achieves the same motion. But here it not only saves space but also gives us continuous operation. In a plate cam or a wedge cam, we'll have to wait for the plate or wedge to come back and start all over again. Not the case with disc cam. Of course you can see here the acceleration greater than gravity will not be possible. So we use this cylindrical cam where the profile is cut on the surface of a cylinder like a channel. So it is not only capable of pushing it up but also pulling it down. So these are some of the different types of cams commonly used. One last remark about velocity and acceleration. One might think we have just achieved the displacement against time graph. What about velocity and acceleration? Well, they are not really independent quantities. Since velocity is the derivative of displacement with respect to time, the slope of the displacement graph determines the velocity. Wherever the slope is maximum, velocity is maximum. Wherever the slope is zero, the velocity is zero, and so on. Same is true for acceleration because that is the derivative of velocity with respect to time. So wherever velocity graph slope is zero, the acceleration is zero. Where the slope is maximum, acceleration is maximum, and so on.